Good morning and welcome to Kennedy Space Center for your What's on Board briefing, where we will have more than 5,500 pounds of research and crew hardware flying up on the Falcon 9 Heavy rocket on May 1st at 3:59 in the morning. Currently, we have a room full of our packed social media invitees here at Kennedy Space Station Television Studio to learn about what's on board this Falcon 9 rocket. Who's excited to learn about the what's on board this rocket? Absolutely, very cool, very cool, very cool. So we have a group of panelists who will come up and explain what's on this payload today, which for this rocket that will be launching May 1st at 3:59. Our first guest is Dr. Kurt Costello. He's an International Space Station Chief Scientist, and he'll be introducing our next panelist. Dr. Costello, come on up.
Thank you. Good morning, everybody. Glad to see you all here, and we're going to be talking about some of the amazing payloads that will be flying to the space station on CRS-17, the SpaceX 17 vehicle. The investigators coming here today are going to be joining some of the 2,600 investigations that have been flown to the space station already. The space station is an amazing multidisciplinary lab platform that we have available to use to advance science, everything from astronomy to zoology. And you'll hear about some of those different uses today with our panelists coming up. They'll be joining almost 4,000 other investigators who've done research on the space station to date, and they will be leaving their mark and returning science that benefits us not only in helping us advance our goals for human exploration in space, but also returning benefits here to the Earth. So first, let's have a short video introducing some of the science on Wednesday's mission. That science looks amazing. Now to hear some more about the scientists and the research going on, let's welcome Dr. Mike Roberts, the Deputy Chief Scientist for our National Laboratory.
Thank you, Kurt. So to pick up on the excellent introduction that Kurt did, the International Space Station National Laboratory is proud to be a partner with NASA in offering research opportunities on board the International Space Station. For those of you who haven't heard of the National Laboratory before, our focus is on providing access to the space environment for research and technology development that has direct benefits here on Earth. So it's been a very busy time for us. Just a little over 2 weeks ago, we launched several payloads primarily in the materials sciences realm out of Wallops Island on an NG-11. We're very excited today to be sponsoring several payloads that are going to the International Space Station that range from student-directed science payloads to payloads that are in partnership with other federal agencies, and those research efforts are directly designed to address the needs of those agencies. So I have a brief video that I'd like to show that explains some of the exciting science that's going up to the ISS National Laboratory this Wednesday morning.
The International Space Station U.S. National Laboratory has a variety of payloads that are packed and ready to launch aboard SpaceX's 17th resupply mission to the International Space Station. Many of those payloads represent life science investigations, all with the intention of improving patient care back on Earth. Let's get an idea about some of those investigations that are associated with this mission. The ISS National Lab is partnered with a branch of the National Institutes of Health that is providing funding to support the use of tissue chip technology for research on board the space station to benefit human health on Earth. 4 of these tissue chips in space investigations are launching on this mission. Tissue chips, small chips containing human cells grown on an artificial scaffold to model the structure and function of human tissue, enable better disease modeling and higher accuracy drug screening. In microgravity, human tissue chip models have the potential to accelerate pathways for understanding the mechanisms behind disease and developing new treatments. Pharmaceutical company AstraZeneca is sending the first of multiple investigations to the ISS National Lab to improve patient care on Earth. This project seeks to advance a novel drug delivery system that uses nanoparticles as carriers for drugs to provide targeted and controlled release therapies. Specifically, the research team will evaluate a proprietary method of nanoparticle formation in microgravity toward improved drug formulations that have greater efficacy and are easier for patients to tolerate. This mission also includes multiple protein crystal growth investigations. In microgravity, crystals often grow larger and with more uniformity than on the ground. High-quality crystals provide a more detailed understanding of protein structures, which enables improved structure-based drug design. One protein crystal growth payload from the National Cancer Institute's Chemical Biology Consortium aims to conduct multiple protein crystallization experiments on the space station aimed at drug discovery. The goal is to develop an accelerated drug discovery pipeline that takes advantage of macromolecular crystallization in microgravity. While we highlighted some of the life science research investigations that are part of this mission, the ISS National Lab is driving research initiatives through all walks of scientific life. From physical and material sciences, technology development, in-orbit manufacturing, small satellites, and much more. To get a better idea about the full breadth of research that's happening on the ISS National Lab, visit issnationallab.org and go Dragon.
So we believe there's no better way to kick off the month of May than sending science up to station. We're excited. We hope everybody's ready for an early morning launch on Wednesday. And I'd like to turn it back over to Derek.
Thank you, Dr. Roberts. Our next presenter will be presenting information about the Orbiting Carbon Observatory, and her name is Dr. Anne-Marie Eldering. Dr. Eldering?
All right. Good morning, everyone. So glad to see you here. Love doing the NASA social conversations. So let me tell you about the Orbiting Carbon Observatory 3. This is a payload that's going to be on the GEM exposed module. So it's hanging on the outside of the ISS looking down at the Earth. And what are we doing? We're trying to measure atmospheric carbon dioxide. So I'm going to give you a little background. I have a figure here that's the Keeling Curve, or a measurement of carbon dioxide since 1958. You may be familiar with this. You see two things here. The black line's just going up over time. That's our increasing atmospheric carbon dioxide amounts. There's a red line, and that's the more monthly numbers. So every season, there's a change. We have plants growing in the spring, and they take carbon dioxide out and draw down the carbon dioxide. Leaves fall off in the winter, and that carbon dioxide goes back in the atmosphere. So that's why that red curve goes up and down. And why is it increasing? Because humans keep adding carbon dioxide in. We're burning fossil fuels like gas and coal and oil, and it's increasing. But the plants are actually doing us a huge favor. Those plants in the ocean take about half of the atmospheric carbon dioxide that humans emit out every year. But some years it's 20%, some years it's 80%, and we've got to figure out why that is. If we want to know what's this going to be in 2050, we have to understand the processes. Which part of Earth is changing? Which part, is it driven by weather, by precipitation, by drought? So that's the kind of science we want to get out of this mission. And I'll just show you quickly a little movie. So OCO2 has started collecting atmospheric carbon dioxide data. We've been doing that since 2014. OCO3 is meant to continue that record of carbon dioxide and build on to what OCO2 started. So just briefly, how the heck do you measure carbon dioxide from space? So I've got a figure here that gives you the principle of our measurement. We just take reflected sunlight that's bouncing off of Earth's surface. If we could Cue up that still, great. So this sunlight bounces off of Earth's surface and up into our instrument, and you might know every molecule has a unique fingerprint or way that it interacts with light. So if you carefully measure the light where carbon dioxide is absorbing, you can see it change. That tells you the carbon dioxide amount has changed. So that's the idea of how we measure from space. And we also want to go to space because we want to see the whole globe. We want to see over the oceans and the land, and we can do that from the space venue. So the International Space Station, though, is a brand new place. So this payload is just a 1/10 scale to give you some idea of what our payload has in it. And we call it a carbon copy of OCO2 because in here, this spectrometer is the same spectrometer as the OCO2 spectrometer, so it's going to get the same type of data, the same light measurements as we have on OCO3. But being on the space station is a little bit different. You know, it's in this precessing orbit. Every day it goes over your head a little bit earlier in the day. And why do I care about that? What I told you, plants were really important to the natural carbon cycle. And plants respond to sunlight as well as temperature and water. So light amounts change over the course of the day. Water availability might too, and we can see that. We've got one other still I wanted to show you here about the plants. So not only do the plants respond to sunlight, but they actually give off a little light when they're doing photosynthesis. And it turns out the light plants give off can be seen with our instrument. So this is a image that was taken with a UV sensitive camera, but you see how those leaves are red, and that's basically an indication of this light that they give out at short wavelengths when they're doing photosynthesis. So we look at that and see how they're behaving, and now we can do that over different times a day. It's going to be really informative. And the last thing I wanted to tell you about is on this payload, I said we're a carbon copy with the same spectrometer. We actually have something here that's called the pointing mirror system. When we want to look at our validation sites, we have to be able to point to them specifically. We did that with the whole spacecraft on OCO2, but we're going to do it with the pointing mirror. And this movie shows you a new way we're going to use that pointing mirror. We've actually devised a method that over 2 minutes, we move our pointing mirror through a set of positions. It scans out data. We get 5 stripes of data next to each other, covers about 50 miles by 50 miles, and each little footprint is a mile by a mile big. We'll have these detailed little snapshot maps of carbon dioxide and SIF that are unlike data we've collected before. Let us see new things about forests, crop areas. One of my scientists wants to look at volcanoes and see if they have a CO2 plume. And of course, there's folks who want to look at cities and power plants. So the snapshot map's going to be a great new way to get a detailed picture of carbon dioxide. So we're super excited. We cannot wait for the first of May to arrive, get OCO3 launched, and eventually get robot arms to take us out of the Dragon and install us on the GEM-EF. It's going to be awesome. Thank you.
Awesome, awesome, awesome. Are there any questions for Dr. Eldering? Yes, sir.
When you're measuring carbon dioxide, are you talking mostly ground-based measurements, or is it the entire atmosphere?
Yeah, that's a great question. So when the sunlight reflects off the Earth and comes back to us, we're actually sensitive pretty uniformly throughout the atmosphere. So we get what we call a total column measurement of carbon dioxide. It's about an integrated amount in the atmosphere.
Just to follow up on that, when you're coming up with like a parts per million measurement, is it basically a kind of an average value for that entire column?
We measure the amount of oxygen, we measure the carbon dioxide, so we get that ppm. We basically have a measure of sensitivity, so a scientist who wants to use it actually can look at where that sensitivity was. It's about like an average number for the total column. And that's good for these global questions. You want to see not just that surface part, what's happening throughout the atmosphere.
Any other questions for Dr. Eldering? Gentleman in back, just stand by for the mic.
So could you just kind of explain whether or not OCO3 is going to be flying in the pressurized or unpressurized section of Dragon, and how the installation process into GEM kind of works?
Yeah, thank you for taking my lead there. So the GEM-EF is the exterior exposed, it's like Japanese experimental module exposed facility. We're just going to be hanging out on the very front end, and we actually get plugged into that GEM-EF here. So the astronauts don't touch our payload, but they will be using the robotic arms. a grapple fixture here and another one here, the robotic arm takes us and removes us from the Dragon, and then we get handed off to a different robotic arm that actually brings us around and then plugs us into the GEM-EF. So through 2 robotic arm movements, we get taken from the Dragon and plugged in. And power, data, and cooling fluid all interface to us through the end of the payload. It's pretty cool. There'll be a movie. Check it out.
Are there any other questions for Dr. Eldering? Okay.
All right,
Dr.
thanks,
Eldering,
everybody.
thank you so much for your time. Very
Thank you,
impressive
Derek.
presentation.
Thanks.
Okay, our next presenter is Dr. Kristen John, and she is the Hermes Principal Investigator.
Great. Thank you so much for having me. I'm really excited here to talk about the Hermes Research Facility that's going to the ISS and Hermes Cassette 1 payload. So I'm Dr. Kristen John. I'm from NASA Johnson Space Center from the Astro Materials Research and Exploration Science Division. So we're actually a planetary science group. So we're interested in studying planetary bodies. So in particular, my research of focus is on studying asteroids. So the goal of Hermes is to study the surface material of asteroids. And this is something that we call regolith. So if you look at asteroids or if you look at the moon, you'll see this layer of regolith covering the surface. So it's this fine particles, fine dust that covers the entire surface. And so you'll find this regolith on airless bodies, bodies that don't have atmospheres. So what's happening is the solar system is very dynamic, and we have asteroids and meteoroids moving around and impacting different bodies. So on Earth, this happens too, right? But what happens is because we have an atmosphere, the particles come in through the atmosphere and mostly burn up. When they make it all the way to the ground, that's when we have a meteorite. But on an asteroid, this doesn't happen because we don't have an atmosphere. So the surface is getting bombarded all the time. So you have this fine layer of fragments on the surface. So that's what we're interested in studying. So that's what regolith is. So why would we want to study it, right? And why would we want to study it on the ISS? So there's a lot of interest in one day sending astronauts to asteroids, for instance. And we have already sent a lot of robotic missions to asteroids and plan to send more. And I say we being NASA as an agency, but also the international space agencies as well. And so every time we visit these asteroids, we learn more and more. And there's very diverse bodies of asteroids. Every asteroid seems to be different. And so we would need to understand how to interact with the asteroid surface. So if you're going to anchor to the surface of the asteroid, for instance, you need to understand how to interact with the regolith. So that's one of the reasons we study asteroid regolith in particular. So why would we do this on the space station? So the space station, turns out, is a very great place to study asteroids and to study asteroid regolith. So asteroids are pretty small bodies, some of them are larger, and so they have actually microgravity levels of gravity. And so this is actually what you find on the space station as well. And then the station also offers long-duration exposure to microgravity. So there's nowhere else that we can get access to long-duration exposure to microgravity. So for that reason, we decided to build this experiment for the station. So if you pull up the first picture, first, I'd like to point out some of my team members. So we have Pedro Curiel, who is our systems engineer, James Brown, who is our manufacturer, myself, Veronica Salcedo, who is the project manager, and Kenton Fisher, who is the vacuum system lead. So this was our team out of NASA Johnson Space Center. Not pictured is our amazing intern, Alyssa Shava-Lithamrong, who was with us for a year from University of Nevada at Reno. So the team at Johnson Space Center led the development. We worked with partners from University of Central Florida and Texas A&M University as well. So what you'll see is, again, talking about why do we want to study this on the ISS. So it's not just the long duration exposure and microgravity. It's also something that we have on asteroids is vacuum, right? So we want to expose our experiments to the vacuum of space. So we're on the space station. How do we do this? Well, space, right? We have the vacuum of space. So we actually have our facility hooked up essentially to a port to space. So through a series of piping and hoses and transducers and valves, we have a really impressive vacuum system that was led by Kenton Fisher. So if you go to the next slide, you can see the picture up on the right. That's the Hermes facility. So that's one of the things that we're launching on Wednesday. So this is an express rack locker. So it's about this big, and this goes in one of the express lockers on station. So this will be a permanent facility on the space station. And the idea is that we'll send different science packages that are called cassettes that will go inside the facility. And so these cassettes are, these are the science packages that the investigators create. So our team also created Cassette 1, the first set of experiments. So it's actually 4 experiments inside of the cassette, and I'll talk more about that in a moment. So we did Cassette 1, but the idea is that Hermes will be open to other investigators. So Cassette 2, Cassette 3, Cassette 7, these will be other researchers that will apply to use Hermes to do research on asteroid regolith and granular material investigations. So if you go to the next picture, So what you actually see is now the door is open, right? So you can see the empty volume inside. This is where the cassette gets inserted inside of the locker. And so about a third of the volume of the locker is electronics and equipment that will stay as part of the facility. But most of the volume, 2/3 of the volume, is for the science experiments. So talking a little bit more in particular about the science experiments. So you can see in the picture on the left, that's cassette 1. There's 4 experiments, and each one is a tube. So it's a clear polycarbonate tube about the size of a Pringles can. And so inside this tube, we have the Asteroid Simulants. And so this is what we're actually studying. And so the main piece of data that we're getting is the movement of these particles. So we have a camera looking at each of these tubes, a small camera, almost like a GoPro type camera. And so what we have is on launch, we have a device inside called an entrapulator. And this device holds the material in place so it doesn't shake around during launch. Then when we get up there, we move this device back, and then the particles can move inside the tube. And the cameras are taking pictures of these particles moving. And so over the course of about a year that cassette 1 will be up there, we'll get this basically time-lapse imagery of the particles moving. And so we're looking at the long-term effects of microgravity and what's happening to the movement of the particles. So one thing that's also really interesting about Hermes is the tools that we have. So I mentioned we have 1 cassette equals 4 experiments. Well, inside each of those experiments, you can have up to 7 tools. So a tool can be really anything that meets our electrical and thermal interface requirements. So for cassette 1, we have the entrapulator as one of our tools. We have a vibration motor that can actually shake the material around. We have a lot of force sensors and load cells that can take measurements of the particle forces inside the tubes. But a future cassette, say cassette 4 or cassette 8, could have totally different set of tools. And so that's something we integrate on the ground and then we send up. And so it's a really robust system that's really interesting. So if you go to the next slide, you can see a picture of the asteroid simulants up close. And so you can see the different particles. A lot of the simulants that we use are silica glass beads. And at the end of all this, we take some of the data and put it into computational models to understand the behavior of the particles. And so one of the things, too, that you'll notice about this experiment is, so you can see the cameras looking at the different particles. And so if we were, for instance, on the ground and wanted to change how frequently we were taking pictures, we can do that from the ground. So Hermes has a really capable system that's all done from the ground. So if I want to change how frequently I'm taking pictures, we just go to our ground station in Houston and send some commands. Or if I want to move my little entrapulator device to move the material around, we can do that from the ground. Or if I want to move our vibration motor to shake the material, all that's done from the ground. So very limited crew involvement. So the astronaut involvement is much simpler than OCO3. It's basically the astronaut will come, install the facility, install the cassette, flip a few switches, and then we're done. So after that, it's all done from the ground, which is pretty exciting. And so this really robust electrical system was led by a company called T-Star that gives us a collaboration with Texas A&M University. And so we got to work with some professors and students there. I think the ISS is a wonderful place to study asteroid regolith, to study lunar regolith in general. So we're excited about the opportunities that Hermes will bring for researchers in the future. Thank you.
Are there any questions for Dr. John? Yes, ma'am. Wait 1 second for the mic, please.
On the data collection, are you collecting that annually, or is that real time, or how often are you collecting?
Yeah, that's a great question. So data retrieval is near real time, not exactly real time, but close to real time. So we have scheduled sessions that we can have as frequently as we want. So at first we'll probably do it daily. Once we get into the rhythm, maybe we'll do it weekly. When we do this, we have to be present at our ground station to pull the data down. But right, so we have a backup system to collect all the data so that at the end of the experiment we have it all in one place just in case. But we actually have a redundant command and data handling system. So we have 2 ways to get data up, 2 ways to get data down. So we utilize some of the things that the space station has in place. So we utilize some of those tools and worked with our team at A&M and some folks at JSC to build a really robust system to pull data down and send commands up.
Are there any other questions for Dr. John? 1 second, sir. Let's wait for the mic.
So what kind of particles do you send in this first cassette?
Yeah, that's a great question. So perfect. If you pull up that picture, so there's 4 different tubes. So 3 of the 4 tubes have silica glass beads. So you can see those are the more colorful ones. So they're silica glass, and each of the different colors represents a different particle size. So one of the things we're interested in studying is particle size sorting, and we're looking at the effect of size and shape. So a couple of the tubes have completely spherical beads. So they're all the same material, but the different sizes, the different colors are different sizes. But then if you look at the second one, the real pretty tube there, that's actually got the same size distribution, but they're basically shards. And so they're angular pieces of glass. And so then we can see the effect of both shape and size on the way that the particles move. And the reason we're interested in doing this is because if you look at the asteroids that we've visited and other agencies have visited, every asteroid looks different. And you always see boulders on the surface of asteroids. And we want to understand, is that representative of the whole body, right? So you have to kind of get rid of this notion that an asteroid is a monolithic singular rock in space. Sometimes they are, but a lot of the ones that we visited are what we call rubble pile asteroids. So it's actually a bunch of rocks held together by their own gravity. And so we want to know what's happening. Are the larger particles moving their way to the top, which is something that we see on Earth, or is there some other force that's causing these bodies to deform?
Are there any other questions for Dr. John? Well, let's give her a round of applause for her presentation.
Thank you.
So our next presenter is Dr. Lucy Lowe, and she will be talking about tissue chips. Dr. Lowe?
Good morning, everyone. It's wonderful to be here, so I hope I can inspire and excite you with stories of tissue chips this morning. So my name is Lucy Lowe. I work at the National Center for Advancing Translational Sciences, or NCATS, which is one of the 27 institutes and centers which make up the National Institutes of Health. And we're delighted to partner with the International Space Station National Lab on a program called Tissue Chips in Space. So I'm going to tell you what on earth are tissue chips and why on earth, you see what I did there? Why on earth are we sending them to space, right? So this is a tissue chip. This is a tiny bioengineered device that contains living human cells that are designed to recreate the structure and function of your tissues in your body. Could be your tissues, could be your tissues, could be your grandma's tissues. All of these cells can survive and live in this environment. And the idea is that we can use these to model diseases so we can understand better disease pathologies and how disease begins. But we can also test drugs or treatments or therapeutics in this system in a way that is not testing them directly in humans or in animals, but we can get really quite realistic results from testing the human tissues in these tissue chips. That means that we can understand better not just diseases, but also how drugs will affect human tissues. So we see tissue chips as a tool to help understand diseases and speed the process of drug discovery, which down here on Earth right now is extremely expensive and takes a really, really long time. So that's what a tissue chip is. This is an example. It's just gorgeous. But why are we sending them to space? So we've partnered with the International Space Station National Lab. We're using microgravity also as a tool because, as you know, microgravity causes changes in physiology in astronauts that often seem to mimic what's quite similar to some disease states or aging here on Earth. So, for example, astronauts might suffer from reduced muscle mass. They seem to suffer from loss of bone density. They have changes in their immune systems. They have changes in their cardiovascular systems. And so that happens on a really short time scale. So using these tissue chips, we can model those kinds of changes on a really, really short timeline that might take months or years or even decades to become a clinical problem down here on Earth. So we're essentially able to speed up the whole process of disease modeling and testing of drugs by using these tissue chips up on the space station. So that's a big win down for us here on Earth. So another big win out of this program is the fact that all of our researchers have partnered with implementation partners, and they're collaborating to adapt these chips so that they can get them up to the space station. So right now, the infrastructure that's needed for one of these chips might be the size of your kitchen refrigerator. And NASA tells us that we're not allowed to send up multiple kitchen refrigerators because they're too heavy and they take up too much space. So all of our teams have had to adapt their chips to make them much more automated, much smaller, and almost turnkey. So essentially, when they get up to the space station, the astronauts can just plug and play. Not only that, but these chips also have to survive the rigors of launch. They've got to be shot up on a rocket and then also survive splashdown at the end. So all of these technological advances and the problems that the teams have had to encounter to shrink their technology and make it really robust is going to be transformational for the technology back down here on Earth, because it's going to make this technology much more broadly accessible to a wider audience who can use it down here on Earth. So that's why we're excited about tissue chips in space. So we have 4 projects that are launching on this next launch on Wednesday morning. I'll tell you a little bit about those. We have a team that is launching a knee joint from MIT. and they're going to be looking at some of the molecular and cellular changes that occur as a result of microgravity after post-traumatic osteoarthritis type injury. We have this team actually is launching this gorgeous chip from the University of Pennsylvania. This is actually a lung and bone marrow chip, and they're actually going to be infecting the lung with bacteria up on orbit and looking at how the white blood cells of the bone marrow mobilize in response to that, which is going to give us some really interesting insights into the immune system and the immune system response. We have a team from a company called Emulate, which is going to be launching a blood-brain barrier on a chip. So the blood-brain barrier is a dense mesh of neurons and supporting cells and vascular cells, your blood vessels, that essentially keep the mushy lump of cells that is your brain safe from chemicals and toxins and other drugs that are circulating through your bloodstream. And so we're interested to see how microgravity is going to affect the integrity of that barrier, which is going to translate into understanding how drugs might cross that barrier down here on Earth. And then finally, we have a team from the University of Washington who is going to be sending up a kidney chip. And Ed Kelly is going to tell you more about that chip in just a second. But I'd be delighted to take any questions. If you want to check us out on Twitter, the hashtags that we're using are hashtag #TissueChips and hashtag #ChipsInSpace. So thank you very much, everyone.
Do we have any questions for Dr. Lowe? Go ahead, sir.
Yeah, I'm just curious to know, personally for you, what would be a dream scenario outcome of this? Like, say we met 2 years from now, would it be that this was a big leap forward in like disease detection or something like? Just
that
personally for you.
A great question. I could go on for hours about what the dream outcomes would be, but I'll highlight just one. So all of our teams have the opportunity to fly twice. So they're launching the first flight, and that's validating the system, that's looking at what insights they can get from microgravity. But the second flight opportunity, they'll have the opportunity to test drugs in the systems. So what we could see would be a huge win, would be if they get an insight from the first flight that means that they can feed the results from that into the second flight and look at testing a new drug in this system that works really nicely, that then can directly translate down to clinical practice much faster here on Earth. Now that process right now, because of the way that the terrestrial drug process and approvals works, could take a really, really, really long time. But because we can see on a really short time scale how fast the tissues are responding, that would be a huge win. The other huge win is the technological advancements. So the teams have done phenomenal jobs of adapting their platforms to make them space ready. And I'm really excited to see how those technological advancements are going to translate down for the teams and for future users of tissue chip technology here on Earth.
Are there any other questions?
Just curious, how hands-on is the crew going to be on board with actually doing the testing? You're saying they're going to inject some of the cells with disease to see how white blood cells react. So how can you explain that process, or how hands-on they are?
Yeah, so the crew will not be getting their hands dirty with any of the bacteria. So there's levels of containment that they have to abide by. But what happens is this is part of the automation process. So all of the chips are primed and ready to go. So I think the biggest input that we have from the crew is actually that they'll be changing some pumps during some of the process over the course of around 2 weeks of each of the experiments. But mostly these are pretty automated experiments now. So we were told that we had to make them, this was their words, not ours, pilot-proof, so that someone as inexperienced in life sciences as an astronaut would be able to do these experiments and not mess them up. So we've made them very, very straightforward, but again, this is all part of that technology translation aspect that's going to make it much more broadly accessible here on Earth.
Any other questions? Go ahead, ma'am.
Hello. My children are watching at home, and my 10-year-old son has a question that's pretty basic, but I think still a good one. How many of each tissue sample are you sending to space?
Amazing. And hi, kids. Great question. So each of our teams has multiple replicates because science takes, you have to do it lots and lots of times to get a good result, right? So this just chip in its own has six of the bone of the lung and 8 of the bone marrow replicates, and then they're sending up 2 chips. So your son can do the math on that one. Ed will tell you a little bit more about his system, which has lots more replicates than that. But we essentially have anything from around 12 replicates up to 72, I think. So we should be getting lots and lots of exciting data from these chips.
We have a question up here in the front.
Hi, I'm somewhat curious about, I know you mentioned the immune issues, if there was any application towards autoimmune disorders on Earth?
So that's a great question. And right now with this experiment, there's not going to be an autoimmune component as such, but everything we learn about the immune system will feed into further research in that area. So the way that we always like to say is that every experiment is part of a jigsaw puzzle. It adds an extra piece. So there might well be opportunities to do autoimmune style experiments with this chip in future. And actually that the bacteria that the team are going to be infusing, which is Pseudomonas aeruginosa, actually is more virulent and can cause more damage to patients who have a compromised immune system and potentially autoimmune diseases. So long story short, yes, there might be some direct applications for that in future.
Okay. Hey, Dr. Lowe, I just want to tell you I really appreciate your time speaking with us today. And I'm going to be very frank, when I heard tissue chips, my mind automatically went to food. But I think, but I think your experiment will do more for humanity than my appetite. I just want to let you know. Okay.
We hope so too, Derek, but
okay.
Thank you.
Let's give her a round of applause. Okay, so we're going to continue to talk about tissue chips, and our next presenter will be Dr. Edward Kelly.
Thank you. So I'm very excited to be here. So my name is Ed Kelly, and I'm a professor in School of Pharmacy and also an investigator at the Kidney Research Institute. So in the first picture, so what you see is a drawing of, actually it's from a niece of one of our investigators. So we're all born with two kidneys. So our kidneys are actually back here outside of our rib cage. So we're born with two kidneys. And next picture, this is basically a cartoon that shows the functional unit of the kidney, which is a nephron. Each kidney has approximately 1 million nephrons. And what I want to emphasize to you is not only is the kidney very important for filtering our blood and removing waste products via urine, but it's also a key organ involved in the synthesis of a number of different hormones and vitamins. One of those vitamins is vitamin D. When we think about vitamin D, we think about, we get vitamin D by exposure from the sun or vitamin supplements. That's actually a precursor to vitamin D. The active form of vitamin D is actually synthesized in the kidney. And the portion of the kidney synthesized in is the proximal tubule. It's, you don't have to learn any anatomy today, but when we say we have a kidney on a chip, no, it's not a British hors d'oeuvre. When we have a kidney on a chip, it's actually a proximal tubule on a chip. And the reason why we do a proximal tubule is that's the site of the nephron where actually most of the things that we're interested in from a scientific perspective, such as vitamin D metabolism, are occurring. So why are we looking at vitamin D metabolism in microgravity? So what we know from experience is that bone loss in microgravity is highly accelerated, upwards of 10% loss per month. And so what we're actually doing is using this unique environment of microgravity to look at accelerated bone loss, i.e. osteoporosis. And so we actually hope to learn in a matter of a course of weeks is how does osteoporosis by vitamin D metabolism occur in a disease which typically takes place over the course of years, if not decades. So next slide, please. So this is the Nordis bio-incorporated kidney on a chip. And so what we have in each one of these chips is small tubules of kidney cells. And so we're actually going to be sending up onto the space station 24 of these chips. What are the advantages of actually doing organs on chips versus, say, doing studies in people? So we recently learned a lot from the twin study of Mark and Scott Kelly, no relation. But what we learned actually is a lot of different things occur in microgravity. But in studies in people, we have a limited access in terms of the biological samples we're looking at, things like blood and urine. You certainly can't look at kidney biopsies on astronauts in space. And so we can actually learn from the system is a lot more of what's going on at the cellular level in these systems. So this is a great advantage of looking at this. And so we're actually sending up 24 of these chips to the International Space Station. So that's 72 individual tubules. Because of this large number of chips that we're actually sending up to the space station, we're actually looking at biological variability in that we're looking at 4 individual kidney donors, 2 males and 2 females. And should also emphasize that the cells we use to populate these are actually coming from surgical waste. So in no way, shape, or form are we actually compromising the access of healthy organs, kidney organs, for donation. So next slide, please. So one of the things that actually Dr. Lowe referred to is the challenges of working in microgravity. taking the systems that we've developed in our lab and actually get them into a point where we actually can do them on the International Space Station. And so you're looking at here, if we're looking at 72 chips in our lab, you're basically going from 48 cubic feet down to less than 2 cubic feet. So this is a gigantic challenge. This is something we've actually had to spend the past 2 years to address, which has been no small feat. And that's actually greatly enhanced by our implementation partner, Bioserve Space Technologies. So one of the questions came, what is going to be the crew's, the astronauts' role in doing our experiments? And so what we'll be doing is our experiments take course over approximately 2 weeks in orbit. And so there'll be 1 week of maintenance, then 2 weeks of exposure to our test article. And so what the astronauts will actually be doing is simply taking our systems, which are actually loaded on the ground, and actually basically popping out media cassettes that contain normal media for maintenance for the first week, and then putting in cassettes that actually have our test article. For example, vitamin D precursor, or normal human serum, which is another experiment we're looking at. And so they're going to be simply taking things in and out, plopping them in and out. They'll do the course of experiment. At the end of the experiment, they'll put in a cassette with a preservative, and then they actually will then go into the fridge or the freezer. And so since it's a very complicated procedure to make these chips, all the cellular and tissue engineering has actually been done on the ground. And so essentially it's going to be launched up, and that would be the all the work that has to be done on the space station. So next slide. So that's our mission patch. Thank you. Happy to take questions.
So do we have any questions for Dr. Kelly?
We're sending up 150 to the International Space Station. But we cannot actually sell them. That was part of the contract.
Any other questions for Dr. Kelly?
How does the tissue stay alive in the card, in the chip, sorry?
So important thing to actually emphasize with pretty much most all of these organs on chips is they all have flow. So flow is a critical component to maintaining good cell viability. And so just as you see in the normal nephron, basically urine and blood will actually flow through there once. And so we have a 3D and microenvironment in there. And so when we put flow through those chips, we can actually keep those out in excess of 4 weeks. Whereas those same types of cells in a standard petri dish would basically senesce or die within a week.
Let's take the young lady right here. Right.
Hi. I just have a quick question about re-entry. So let's say that the chips get damaged in re-entry. Do you guys have any alternative data collection that you would be using?
So fortunately, so at the end of the experiments, the cells will either be affixed with formalin, or they'll actually been put into the minus 80, so they'd be frozen. So at that point, we're not really worried about containment. One of the things we were truly worried about was launch. So these are a tubule of cells, and so you see about 5 Gs for about 10 minutes to get to low Earth orbit. So one of the first questions we asked ourselves was, are we just going to get collapsed tubules? And so that's one of the very first things we ran in our lab, and no, we don't. We actually took them up to 20 Gs, and they did fine.
We have a gentleman in the second row back here that has a question.
I'm curious more on logistics. I mean, you talked about how they keep them around for up to 4 weeks. How early are they integrated into the Dragon capsule to get prepared for launch? Is that something you do pretty late, or is that something you can do?
Yes, it is something we do pretty late. We're actually doing it at 2 o'clock in the morning. Yes.
Okay, do we have any other questions? Well, let's give Dr. Kelly a round of applause. Okay, our next guest is Dr. Mike Roberts, and he will be talking a little bit about genes in space 6. Dr. Roberts?
Thanks, Derek. So now's your chance to go, oh no, again. So what I'm doing this time is I want to introduce another one of the experiments that's going up to station. And this one's a little bit different. We, at the International Space Station National Laboratory, have many partners, and we're equally excited by all of them. And the tissue chips, I think, is the coolest science you're ever going to see go. So we're looking forward to great results from that. But even more exciting to us at ISS National Lab are opportunities where we have to engage with high school students, with students in elementary schools, with students who, as you've already heard from today's sessions, have very good questions that are based in science. And there are excellent concepts that come out of that pool, those thoughts, that can be translated into excellent science return. So you're going to hear a little bit more about those, and I wanted to introduce the program that they're involved. So you've heard a lot already about chips in space. There's another program called Genes in Space. Genes in Space is a science, technology, engineering, and mathematics educational program that is available for students to write project descriptions for and win an opportunity to do research on the International Space Station. We operate that program in partnership with Boeing. So Boeing, in addition to maintaining systems and sustaining engineering on board the International Space Station, has been actively invested for many years in promoting science and engineering and technology development using the unique environment of space. Genes in Space utilizes a platform called the mini PCR system. PCR is polymerase chain reaction. Polymerase chain reaction is essentially the ability to act as a copy machine for DNA. And for the first time this year, the team that I'm going to introduce is not only using that copy function that's available to them, they're actually going to be doing sequencing on orbit. So we now have the capability on board the International Space Station to not only use the tools of molecular biology that enable us to make copies, we're actually able to go in and look at the changes that are induced in response to the space environment or changes that are induced by the engineers themselves who are seeking to better understand the way spaceflight influences the performance of cells and human health in those systems. So the team that I'm going to bring up now is from the great state of Minnesota, where they have informed me that winter has indeed come. So they are very glad to be here today, and I would like to bring on stage the Genes and PCR winners from 2018.
So thank you for having us here today. I'm Arthi.
I'm David.
And I'm Michelle. And I'm Rebecca. And we are the 2018 Genes in Space winning team. So if you're unfamiliar with Genes in Space, it's a 7th to 12th grade DNA competition where you design an experiment to take place on the International Space Station. So today we're going to be talking a little bit about our experiment, which involves investigating DNA repair in space.
Can I have the next slide, please? The one after that. One more slide. Oh, thank you. So DNA is the blueprint of life, right? So it encodes all our genetic information, and it gets transcribed to RNA, which is translated to proteins, which of course help all of our cells function. Unfortunately, DNA can also break sometimes, and since it's so important, it's really important to maintain the integrity of the DNA. And so since it's such a deleterious process, we wanted to study how these breaks are repaired in space. There are a few primary mechanisms cells use to repair these breaks. The most common one is actually error-prone, so it can introduce mutations which harm the cell. There's an alternative pathway which is error-free, but you need a special repair template. Can I get the next slide? So this relates to astronauts in space because astronauts undergo high radiation from HC ions or galactic cosmic rays, which can lead to these double-stranded breaks. So it's really important for us to learn how repair pathways function in space and what the relative frequency of these pathways are to avoid having errors in these astronaut cells. So therefore, if we can figure out the relative frequencies of these repair pathways, maybe we can choose the right drugs to mitigate erroneous DNA repair. So our objective in this experiment was to examine how repair pathway frequencies and double-stranded break repair as a whole are affected by microgravity. And we hypothesized that the error-prone pathway will actually increase in space relative to the error-free pathway. Can I get the next slide? So to test our hypothesis, we're going to be using the CRISPR-Cas9 system, which has been adopted from a bacterial immune system for use in many other organisms, including humans. The analogy I like to use is that of a book. So if I want to edit, say, the text in some paragraph in a book, I can change a word, add some words, or remove some words. And CRISPR-Cas9 lets us do this with the 3 billion letter book that is the human genome. So Cas9 is a protein that serves as like a pair of scissors. So it allows us to go in and make a specific cut somewhere in the DNA, which is then fixed by the cell to insert DNA, remove some DNA, or change the sequence of the surrounding DNA, much like you would do in a book. And you can choose exactly where you're going by changing the sequence of this guide RNA. And since it's so useful, it's really popular as a tool right now in biology, and it's very cost-effective as well.
So CRISPR-Cas9 is extremely useful in our experiment because it allows us to choose a specific target site and look at the DNA that repairs itself there. So after the DNA repairs itself, we can look at it and see if there are mutations, which means that the error-prone pathway was used. And if there are no mutations, we know that the error-free pathway was used. And a big advantage of CRISPR-Cas9 is that while standard radiation would induce breaks at random locations all over the genome, CRISPR-Cas9 allows us to choose the cut site and make a controlled cut at that site. And it's a lot easier to find typos in a specific paragraph of a book than in the entire book. So next slide, please. So in our experiment, we want to verify that Cas9 can cut in space and that we can deduce repair pathway frequencies based on the resulting sequences. So on the station, astronauts will be doing this experiment in yeast cells, and they'll be using a guide RNA that targets a gene called ADE2. And when ADE2 is cut and repaired, the yeast, which is normally white, will turn red. And this visual signal allows us to verify that Cas9 has cut. Next slide, please. So this is our procedure, and the first step that astronauts will do on the ISS is to do the transformation. And what this means is that they're just adding all the components necessary for the CRISPR-Cas9 system to work into the cells. And this includes the Cas9 protein, the guide RNA that targets ADE2, and a repair template for error-free repair. And they'll do all of this by inserting a plasmid, which is a large circular piece of DNA. So after the cells have had some time to grow, they'll select the edited colonies, which are the red colonies in the plate. And the red, again, means that the Cas9 has cut this DNA and it's had time to repair. So they'll take these cells and extract DNA from them and then amplify them using this tool called the mini PCR. And so this mini PCR can take the certain segment of DNA that we want to analyze and make a lot of copies of it so that we can sequence it and analyze it. So finally, they'll use a sequencing tool on board the ISS to read the order of the bases in the region that we want to analyze, and we'll be able to tell whether or not there are mutations in the DNA. And once again, if there are mutations, we'll know that the error-prone repair pathway was used, whereas if there aren't, we'll know that it was the error-free pathway. Next slide, please. So the results of these experiments could help set the stage for genomic editing in space and protect astronauts from intense radiation experienced in flight. And what's exciting is that it's also the first time that a lot of things are being done on the ISS. So this will be the first cell transformation on the ISS, the first time an outside group is using the tools and technologies developed by the biomolecule sequencer team at NASA, and the first time that CRISPR-Cas9 is used in space. And last slide, we'd like to thank everyone who helped and advised us throughout this project. Thank you.
So are there any questions for these students? Ma'am, just wait for the mic to come to you real quick.
Hi there. Can you tell us how long you spent developing your experience? And as a fellow Minnesotan, I would love to know where you go to school and what years you are. Thank you.
Okay, so me, I'm Michelle, Rebecca, and Arthi all go to Mounds View High School in the St. Paul suburbs area. We're all seniors. David graduated a year early, so last year when we submitted our proposal, he was the same year as us, but now he's a freshman at MIT.
And you went to Woodbury High School.
Yeah, and you went to Woodbury High School. So we initially entered this competition in April, and we all had biology backgrounds, so we all worked in labs at our state university and had experience doing lab work since like sophomore, freshman year. And we've all been very interested in biology, so once we got started on brainstorming, it didn't take us extremely long of a time to start thinking of ideas, especially since we had 4 people on our team. And after that, we got our results back in May, and we were very surprised to find out that we were finalists. And from April to June, when the ISS R&D conference was, we were basically preparing nonstop, brainstorming on how we could make our proposal better and how to practice public speaking at a conference. Yeah.
And then after the conference, we just worked on finalizing all the details, and eventually it got transferred over to like payload integration, and now it's on the rocket, I guess.
Any other questions for the students here?
I'm curious, you guys all have biology interests and things like that, is there anything difficult that you encountered just by the logistics of going from biology experiments on the ground to having to now launch an experiment on a rocket to the space station?
Definitely. So we were, I don't think we realized how many restrictions there were on the ISS. So after we won the conference, we began developing our experiment so it was suitable to be performed on the ISS, and we realized that there were so many things that we wouldn't be able to do. So originally we wanted to do human cells, but those were too difficult to grow and keep alive in order for us to do the experiment. What else?
You couldn't open tubes.
Yeah.
Yeah, because it's in microgravity. So we wanted to open tubes, but we couldn't. So we had to, make our project fit around the guidelines.
Any other questions? Lady in the front.
So what are you guys going to do next?
Yeah.
What's after this? I mean, this
Hopefully
is huge.
college.
But like life goals, like job, career goals?
I want to do medicine.
Yeah, me too.
Yep, me too.
And I want to do research.
I think we all want you to do that.
I'm excited to see what you got going on next.
Listen, thank you guys so much for your time. Thank you, guys. I hope you guys enjoyed the What's on Board briefing that we had here today, and we are all looking for a successful launch on May 1st at 3:59 in the morning. So let's all say it together on three. 1, 2, 3. Go Falcon 9. Come on, y'all. Go Falcon 9. Go Falcon 9. All right. Signing off here from Kennedy Space Center.